Hi, my name is Chris.
And I'm Mira.
And we are associated members of ML4Q.
And you are listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computing cluster answer questions about their work in the cluster, their research, and the future of quantum.
I would like to introduce Mira, a PhD student at IQI, who is joining me as a co-host. This is our first co-hosted podcast, so it's an experiment.
But I'm a theorist. Nevertheless, I'm excited to be here and talk about all things quantum. I'm looking forward to discuss and learn more about the different research topics in ML4Q. I think it would be so much fun to talk to other theorists about new ideas and learn from experimentalists about the implementation.
That's true. For me, the podcast has just been an amazing opportunity to meet interesting people and talk with them. For today's episode, we left the cluster bubble on a road trip to Siegen, where we met Christof Wunderlich.
But before we discuss with Christof, we want to share impressions from the lab there. I found it extremely fascinating to see the ion traps and have an interactive introduction to trapped ion quantum computing. We also visited EleQtron, Germany's first quantum computing startup. It was a first for me to get to know how a quantum computing startup works. What do you think?
Yeah, indeed. I was impressed by EleQtron's compact setup for ion-trap quantum computers. 2 server racks and an optical table the size of a dinner table. And of course the microwave control paradigm seems magical. Let's hear more about it from Christof himself.
Welcome, Professor Wunderlich, on the ML4Q Q&A podcast. Professor in Siegen since 2005, co-founder and co-CEO of EleQtron, that is with a Q instead of a C, Germany's first quantum computing startup. So we are going to talk about your background and career and how you went from a university professor to a quantum entrepreneur.
First, let me thank you for giving me the opportunity to talk to you here and today in Cologne. That's very nice.
So when did you decide that you wanted to become a physicist?
Okay, so that's I haven't thought about this in a long time. So actually, I was interested in physics already when I was in school. So this was physics and mathematics were my favorite subjects always. But then when it was time to leave school, I was more interested in other things, and so postponed my physics studies for a while. But finally, I came back to physics. And started to study physics in Tübingen, which is in the south of Germany.
And Tübingen is a pretty small university town, right? It's a big university in a small town, sort of, right?
Yeah, that's probably right. Yeah, so it's a very nice town, very lively, little nice town in a nice setting, and lots of students. So. It's nice there to be a student.
And there you did your diploma, but then you went to the US, right?
Yes. So at the time, there was no bachelor degree or something like this. So it was you could divide your studies into diploma and the real diploma, so to say. And so I studied up to the diploma and a bit longer actually, and then. I went to Stony Brook, New York, to do a master's degree. Actually, it was only meant initially as an exchange program, so for 1 year. But then I decided to stay longer and finish a master's degree, and so that was a highly interesting experience.
And then you were back in Germany to.
Yes, so then I came back to Germany to do a PhD. So I went to Munich, to the Max Planck Institute for Quantum Optics. I was lucky enough to get a position with Professor Hensch there. And started to work on a different subject again. So in Stony Brook, I did a master's thesis, a 1-year-long master's thesis actually. So corresponding to the German diploma thesis, which was the prerequisite to do a PhD then in Germany. And yeah, so this was about nonlinear dynamics in a plasma, the master's thesis, and then I started to work on molecules in intense laser fields at the Max Planck Institute for Quantum Optics. So yeah, very different subject, but again, very interesting.
And what got you into this? This is sort of a combination of nonlinear optics and sort of matter interaction, I guess. Was this more from a practical engineering point of view, or trying to find out things about plasma physics? What drove you into this direction?
At Stony Brook?
Yeah, at Stony. Let's start at Stony Brook.
Okay, so I was very much interested in this type of quantum optics and atomic physics things. And in the lab I worked, there was a source for hydrogen ions, and this source behaved in a very strange way. And so it was my task to investigate how this source works. And the source is a plasma, radio frequency plasma, basically. And then, we looked at this nonlinear strange behavior of a plasma. So that was how it started.
So in that case, you use optical methods to find out the plasma physics. So you shoot.
No, actually, the diagnosis was by extracting a beam of ions.
Okay.
Actually,
yeah. See.
So, and measuring a current.
So, like really an electrical current, like the ions.
Yes.
Yeah. See. And yeah, so I guess then you decided to go back to Germany. Was it more going back to Germany, or was it the excitement of going to Munich? And
first, the decision was there to go back to Germany, and then I was looking within Germany for something interesting. And yeah, so the Max Planck Institute was at the time, and still is, a really outstanding place to do quantum optics, atomic physics, laser physics, things like that. So, yeah.
And then what did your PhD work, how was it different from what you did in your master's?
It was very different. So it was a completely different topic. So actually, when I started doing the PhD, the topic was more doing spectroscopy on a certain type of molecules, on so-called excimer molecules. At some point, I got much more interested in a different topic, in how to control molecular structure using laser light. And so my PhD work took a different direction then. So I finished up the excimer work, but then started this work on molecules in intense laser fields, which was also very interesting and new and exciting. And yeah.
How long were the laser pulses then? What does intense laser fields mean back then?
Okay. So I started this. It's basically a new research direction in this group at the time. And so I had to use the things that were available at the time in the lab. So they're only after the experiments I did there, people were convinced that this is really something interesting in the longer term, and then new laser systems were bought and stuff. So I started with a pulse dye laser, where you could reach intensities up to 10 to the 11, 10 to the 12 watts per square centimeter, nanosecond pulses. So it's, from today's point of view, it's a
slow and low intensity.
Yes, yeah. So it's a low repetition rate, long nanosecond pulses, which is, for today's standards, long.
Yeah, we just had the Nobel Prize for attosecond.
Yes, exactly.
Pulses.
Exactly, right. So actually, that's a very interesting question, of course. What is intense? What is an intense laser field? So one has to put this into perspective of the at the time, so we wanted to basically distort the molecular structure of molecules. And in order to see an effect, we had to choose the right molecule that shows an effect at these intensities. And so the choice was a bit an exotic molecule, argon 2+. So it was also molecular ion. But yeah, so it has a very low vibrational frequency, and then when you distort the electronic potentials, you see a strong effect, even at moderate intensities of 10 to the 12 watts per square centimeters or so.
So I guess then you learned the sort of, I mean, this was your like entry into optical tables and lasers and...
Yeah, that's true. So the molecules were created in a molecular beam, actually. So it was a molecular beam apparatus, which where you can have very clean experimental conditions. So you're sure you only have one species of molecules, mass selected molecules, and and then lasers and yeah.
And what were your views at that time on atomic quantum computing? It was probably already starting to brew up, this topic.
Not during my PhD. So, I mean, yeah, so Shor's algorithm was published in 92, I believe, but I haven't heard of this in 92. So, and I mean, the first proposal to actually use a real physical system for quantum computing was the one by Ignacio Cirac and Peter Zöller, and this came out in 95. So that was at the end of my PhD. And yeah, so during my PhD work, I did not think of quantum computing or anything. It was completely curiosity-driven research about how molecules behave in laser fields and how you can control actually the internal structure of molecules by using laser fields.
And did you, like this optical work, to me it's always, because I come from more of a solid state background, I mean the optics work is like this very, very clean physics, right? Like you have optical tables where you control everything. You are you can generate very clean sort of textbook like conditions. Is this the right way to think about the experiments, or are these like, because the molecules, they are sort of they're not so dense, right? Like you really have light interacting with single molecules in sort of a very clean system.
Yes, so also in this molecular beam experiment, you're right. So it's a low density of molecules, and you can think of it as non-interacting, completely non-interacting molecules. So, and it's like, it was an ensemble experiment because
you don't see a single
exactly. Yeah, you don't see a single molecule. But I mean, the way you interpret the experiment and extract the data is you look at the interaction of a single molecule with a laser field, but then you have to average over the orientations of the molecule and so on, because it's an ensemble.
Yeah, and this step from interacting with a big ensemble of identical quantum systems to interacting with a single quantum system, like, did you think about this already during your PhD?
So for the questions we asked in these molecule experiments, it was not really necessary to go to a single molecule. I mean, you need good signal to noise ratio, so it was always clear that one has to work with a large number of molecules, and it's easier. In that case, it was simply not necessary to isolate a single molecule to do such experiments. So at the time, this was not a concern to me. So, but then when I went on as a postdoc to Paris, there individual quantum systems came into focus, really. So photonic fields in a cavity, so in the microwave regime, microwave photons in a cavity. And there it was really about controlling individual quantum systems, individual photons, basically.
Did you at the time think, well, what if I could work with a single quantum system and really sort of, or...
Yeah, so I mean, the questions that were investigated in this lab at the time, they were so fascinating and new. And so the fact that you work with individual quantum systems was certainly one part of the fascination.
Okay. And do you think that the work over there in some way influenced you to go further into atomic research or in quantum computing?
Yeah, definitely. So I mean, so when I was in Paris, there was one can say probably a friendly competition between these cavity QED experiments on the one hand and trapped ion experiments on the other hand. So both were able to work with individual quantum systems to investigate fundamental questions of quantum physics, like measurement process, creating Schrödinger cats and creating entanglement. And so both of them did conceptually very similar things, but with different tools, basically. Yeah.
So that was basically where you got into the sort of quantum computing world, or quantum information, or whatever one wants to call it.
Okay, so at the time, this was still... Okay, so when I started my postdoc work in Paris, quantum information was not on the agenda yet, really. I mean, there was already this proposal by Dirac and Zoller, and shortly after, actually, an experiment from the Dave 1 group where they entangled internal states and motional states of a trapped ion. So as a first step to doing quantum logic with more ions. But yes, it was a phase where this new field of quantum information science was really at its starting point and emerging.
Serge Haroche was not driven by building a quantum computer at the time, but rather by finding out if you can have a single quantum, like interact with a single photon or manipulate it.
Yes, exactly. So investigating fundamental things like entanglement, EPR pairs, and Schrödinger cats, and all these these puzzling questions of quantum mechanics. That was at the center. So at the time, the Paris group was very skeptical about quantum computing.
Okay.
So
it's also quantum error correction was also not yet. I mean, that also came in 95, like in the sort of the full idea for how that you could actually build a quantum computer was maybe was still in development at the time. Say.
Yes. So there was the basic idea that one can trace back to Feynman and even earlier sources, and then there was this Shor algorithm, and then there was a proposal to actually do it in a real physical system, and so it was, and there were many years between these steps. Many years. So 82 Feynman, 92 Shor, 95 Dirac-Zoller, and so it was at the time a slow development still, and something emerging.
And was there a lot of contact between Vineland, like the trapped ion world, and the world of this cavity QED?
I would say yes. I mean, people were in contact and knew exactly what the other one is doing, or exactly, I mean, they knew the type of experiments that are being conducted, and it was I would say a friendly competition from my point of view. That's how I saw it at the time.
So, shall we discuss now trapped ion quantum computing? How do we trap single ions?
Yeah, how do we trap single ions? Okay, so so you need you cannot trap charged particles using only static electric fields. So I mean, the nice thing about ions, about any charged particle, is that they have a charge and you can grab them by using electric fields, but it's not possible to have a 3D potential minimum using only static fields. So what a necessary ingredient for trapping ions was this invention by Wolfgang Paul. So an electrodynamic traps where you have time-varying electric fields, and then you can show that you can really create a minimum of a potential, of a quasi-potential, then in space, and trap ions. Yeah.
This is sort of even a German invention in a way, right?
Yes, Wolfgang Paul, he worked in Bonn, and actually he invented this first as a tool for nuclear physics experiments and high energy physics experiments.
So just to hold it in place and be able to do...
Actually, more like as a mass filter.
Okay. Yeah.
Initially. And so then Hans Dehmelt, he took up this idea of, he was probably the driving force behind trapping individual ions. He was in the US at the time, but he came then to Germany to realize his idea of trapping an individual ion. And so he was driven by the quest for seeing an individual atom, really seeing it, so meaning using his own eyes to see an individual atom. So, and he was, this idea at the time, from what I hear, was not so popular. So, but then he came to Germany and he found, in Heidelberg, he found Peter Toschek, who was an expert in laser physics, and they joined forces to actually try to trap a single atomic particle. So that was quite pioneering experiment. Yes.
There's this sort of Ernst Mach debate early on, right? Where he was where Ernst Mach was always saying, atoms, it's a theory, but nobody has ever seen one. So it was really just to say, okay, here it is. I'm not sure what the driving force for Dehmelt was, if Ernst Mach was on his mind, but in any case, he wanted to see a single atom. And that's why he chose this particular type of ion, barium, because barium has scatters light in the visible range. So it's at 493 nanometers, so it's between green and blue, kind of. So, so where you have a good laser, sort of, I guess. I know he wanted to really just see it with his own eyes.
He wanted to see it. That was the motivation, and then he needed a laser source that delivers this wavelength, and he found this together with Peter Toschek and Werner Neuhauser in Heidelberg, actually. So Werner Neuhauser was a PhD student at the time. He in Heidelberg with Peter Toschek, and both of them later on moved to Hamburg. So,
which was your next station after Paris?
Yes.
So you defected from cavity, QED, and Rydberg atoms to ions in Hamburg.
Yes, exactly. So I again switched As an experimentalist, actually, it's not so trivial to go from cavity to QED to trapped ions. I mean, conceptually, it's quite similar, and for theorists, you just take a different notebook, I suppose, and start doing things. But as an experimentalist, it's it's a different type of experiment with different emphasis and tools.
You were familiar with the lasers and the optical table, but maybe less so with the RF setup.
Yes. So yes, you're right. I mean, lasers were in both experiments, and laser control of internal states of atoms. Yeah, that's a similarity, of course. Yeah. Mm-hmm.
So let's go on in the ions. Let's say you have the trap and you trap the ion, or ions. What is the next step of there's always this discussion of laser cooling. So let's say the ions come in.
Mm-hmm. Yes. So yes, in the end, you want. Thinking about quantum information science, you want to work with a real quantized system. So you need to be able to see also the quantization of the motion of the ion, and you have to control the motion of the ion. And for that purpose, you need laser cooling, that's if you really want to go close to the ground state, you need laser cooling.
The step is you trap the ion, and you basically just have to get it to stop moving, sort of.
Yeah, yeah. And so what you use is the fact that light carries momentum, also linear momentum, and so you can scatter light off an atom or a molecule or something and slow down the motion by imparting momentum to it. Yeah,
that's I would say a bit counterintuitive, in the sense that when you provide momentum to matter, then it would move further. Right?
Yeah, but if you think let's say you think of an atom moving from left to right, and
yes,
your laser beam is moving from right to left, so they are opposing momenta, and then momentum conservation implies that your atom has to slow down then.
And do you think that there are specific elements that make good ions for this purpose?
Yes. So initially, I already mentioned the reason why Hans Demel chose barium. So barium is still today a very popular ion because it can be laser cooled quite well, but there are other ions. Calcium is a very popular ion, which was chosen because it has very convenient transitions where you can use diode lasers, and so relatively simple laser light sources. So there's a number of ions: strontium, beryllium, ytterbium. Our favorite ion is ytterbium.
On which ion did you learn the ropes of ion trapping?
That was barium, actually. Yes, so that was in Hamburg. I worked mostly with barium, but also with ytterbium. And yeah.
So basically, you learned from the pioneers of trapping ions with Toshek.
Yeah. That's right. Yeah. So Werner Neuhauser, he was also there in the lab at the time. So yeah, there was a lot to learn from them. Yeah.
And where were ions at in your time in Hamburg? What did you work on there, and what was the challenges? And
actually, so this was when I went to Hamburg. This was 1997, and there I had in mind. So I went there with the intention to work on trapped ions for quantum computing. That was the mindset with which I went there. And then, of course, first I had to learn how to handle trapped ions, how to trap them, how to laser cool them, and all these things that you just mentioned to detect them properly. And yes, but the intention was to use them for quantum computation. That was the clear direction.
And so in this time, like, how long did it take you to learn to transition to become an ion trapper?
I'm not sure at what point you are considered a real ion trapper. So if there's I didn't receive any diploma on that. So so it's a thing. You start to learn something new, and you never stop learning new things. What you do is you contribute your own thoughts and your own views, and so it's a constant learning process, and you try to contribute something yourself, also that other people can maybe also get new insights.
So could you also elaborate on what are the different ways of trapping ion or controlling them? For example, the most popular one is laser control.
Yes. So now you're going in the direction of controlling trapped ions as qubits, as quantum bits for quantum information processing. Yes. So you need to choose some internal states that work as a qubit. And at the time, the only available control was laser control, so controlling internal states coherently by using coherent laser light. So either two electronic states connected by an optical transition, or hyperfine states manipulated via a Raman transition, so 2-photon Raman transition. So that was this state of the art at the time. And maybe working with ytterbium instilled some doubts about whether this would be a good way to go when thinking about scaling up trapped ion quantum computing, because at the time, so to control ytterbium ions, the hyperfine states of ytterbium ions, and couple them to the motional states, there were no diode lasers or anything available. It was really messy dye lasers. So dye lasers are something you want to avoid if it's possible. So a dye laser frequency doubled, which doubles the complexity, and it needed a lot of caretaking, and didn't seem like an instrument that you want to use for something like quantum computing.
They can lose the lock, or what's the problem with them? Like,
so the problem with dye lasers is, one of the problems is that they use dyes. You basically have a bottle filled with a liquid with some solvent and some dyes in it, and then you have to squeeze this through a small aperture, so you have a small beam of the solvent, and then you direct your pumping light, your laser pumping light, to this small beam, and then you have to exchange the dyes regularly. They mess up your whole optical table if you're not careful. So it's just a very. They need very intensive care and lots of work. Lots of your time goes into making these lasers work properly. So they were not commercially available. I mean, they were all home built, and
so basically you realized that you have this one laser which is doing this transition and this other laser that is doing another transition, I guess. And you realized that why don't I just drive the difference between them directly, or is it too simple?
For quantum computation, what you really need, you need to couple your internal qubit states to the motional states. So you need to be able to, while you change the qubit state, you need to be able to at the same time change the motional state of the ion, because that's the quantum bus that is used for communication between ions. Yeah. So so that's an important thing, of course, we have to mention that. Yeah. So you need to couple internal and motional states. And this is also done, one can look at it in this picture of that photons carry momentum, and then you scatter light on an ion, so you change the internal state and at the same time impart momentum to the ion, and then the ion starts moving in the trap, and then the other ions notice that this one is moving via the Coulomb interaction, because they all interact, they are all charged particles and interact via Coulomb interaction. So if one ion moves, the others notice as well and also start moving, and that's your quantum bus. So the crucial ingredient is you need to be able to couple your internal dynamics to the motional dynamics. And if you use a microwave transition at 12 gigahertz, let's say, if you put in the numbers, you simply realize that there's not enough momentum to set an ion in motion in a given trap. So that's why people always used laser light, because it was the general agreement that to couple internal and motional states, you need enough momentum, and this is not possible in the microwave regime. So so we thought of this in Hamburg, still, of this new concept of, by modifying the ion trap, by including an additional magnetic field, a spatially varying magnetic field, you can actually show that you can then, even with microwave radiation, couple internal and motional states. So, but this requires a modification of your trap. And that's what we thought of at the time, and then started to develop such a new type of trap.
So, and like the idea then is to, instead of controlling the ions with these complicated lasers, to control them with microwaves. Around, like, in the mid to late 90s, early 2000s, you have this whole quantum computing effort with nuclear magnetic resonance, based on molecular ensembles, I guess. And they are controlled with microwaves, with just driving through an antenna. When you developed this, did you think of this type of setup?
I think at some point I realized that what we were developing at the time is very similar to NMR. And this was also a very helpful insight, actually, because, I mean, NMR was extremely successful very quickly. So, there were these proposals for quantum computing, and in no time, basically, NMR people could do quantum algorithms. From today's point of view, it's not sure if it's really a quantum algorithm, but at the time, it definitely looked like...
it was the first Shor algorithm.
Yes, the first Shor algorithm. And I mean, today some people think it's a simulation of a Shor algorithm because there's not really entanglement created. But okay, so that's a different discussion. But at the time, it was firmly believed that NMR does real quantum computing. And this was very impressive. I mean, in this very short time span, they achieved these really impressive results. And the reason was because they had this highly developed radio frequency control and microwave control of nuclear spins. I mean, this, and so, yeah. So actually, we thought of a multi-ion chain. We thought of this like an artificial, or I thought of it as like an artificial spin molecule, where you actually have pseudo spins. So your hyperfine states are like the nuclear spins in a NMR molecule, and then also you can actually show that you get exactly this sigma z type of interaction like in molecules used for NMR. So yes, I thought of an ion chain like a molecule in NMR. Yes, that's but one where you can actually control your coupling constants. So you don't have to take what nature gives you, the coupling constants. You can control the coupling constants, you can control the resonance frequencies, and you can address individual qubits, not an ensemble like in NMR, but really just individual qubits. So I thought of it as a better version of NMR, actually. So.
And wait, at the time, so your background was sort of optics and so on. So, and NMR had already developed like some of the most sophisticated control pulse things in the microwave regime, but you had to pick this up. I mean, this existed, but the control strategy, like how to make the pulses, did you have to learn this at the time then, sort of?
Once I realized that one can actually use microwave radio frequency pulses for trapped ions, for trapped ion quantum computing, and once I realized that this is actually looks like a molecule in NMR, then I started to look into the methods that are used in NMR, I mean, which were not known to me yet before. I mean, of course, you know that NMR exists and roughly what they do, but I wasn't aware of how sophisticated everything was already. So, yeah, that was a nice discovery. Then to see that we can now apply lots of things that are well researched in NMR. We can now use this actually for trapped ions. So, with this new type of trap,
And what were the coherence times that you were observing then, and what sort of gates were you able to implement?
These hyperfine states, they have basically lifetimes that are, for all practical purposes, on every experimental time scale, they are infinite. Basically, they are not infinite, but I'm saying for practical purposes. So they never limit an experiment that you do. if you choose the right hyperfine states. So, but for our experiments, we had to choose magnetically sensitive states because that's this mechanism of coupling internal and motional states using radio frequency microwaves relies on the fact that at least one of your qubit states is sensitive to magnetic fields. And this, of course, the sensitivity also extends to unwanted magnetic fields. So you include a magnetic field in your trap that gives you the coupling, but then you have lots of fields around from the fridge next door or whatever, magnetic fields that are just noise and you don't want them. And they limit the coherence time of your qubit then eventually. So from today's point of view, we have ways of recoding the qubit into magnetically insensitive states. So by simply applying a few microwave pulses, we can switch from a magnetically sensitive state that is coupled to other qubits to a magnetic insensitive state that does not talk to other qubits and is also basically immune against fluctuating fields around. Okay, but yeah, at the time, so the coherence time was limited by these magnetic field sensitive states.
So you knew already that you could sort of, I mean, this is sort of like you can shelf the qubit if you need to not do something with it for a while. You can just, protect it and then you can wake it up and do something with it again.
Yes, exactly, yeah. And okay, and we also developed then, so NMR was very useful in that respect. So we developed our own dynamical decoupling sequences, so certain decoupling sequences were very well known in NMR. So to overcome the decoherence of your qubit states and prolong the coherence times. And so we also showed then continuous dynamical decoupling, so where you don't need pulses, you continuously apply driving fields, and we could extend the coherence time by 3 orders of magnitude. So the limited coherence time, the originally limited coherence time, is not really a concern anymore.
And this technique of radio frequency magnetic gradient ion trap control, you named this MAGIC, right?
Yes. So MAGIC is an acronym for magnetic gradient induced coupling. So that's exactly what's happening in the trap. So we have a magnetic gradient field, and this gradient field induces then, instead of the momentum from photons, induces coupling between individual ions. So you couple your internal state to the motional state, and then via the motional state, the other ions also notice that something is happening to your original qubit.
Could that be thought of as an inherent all-to-all coupling mechanism?
Definitely, exactly. So it's if you have a string of n ions in your trap and you have this magnetic gradient, you can show that you have a coupling matrix. So J coupling, like in a molecule, a different physical mechanism, but still mathematically the same thing. You have your coupling is described by some coupling constant J times sigma z of one ion times sigma z of the other ion of all other ions, and they all talk to each other. So it's an always on, all to all connectivity.
But when you think about scaling this architecture, then there might be certain issues with the all-to-all coupling. So what are the solutions for this problem?
Okay, so you can think of it as a problem, but you can also think of it as a solution. So let me explain this a bit more. So, early on during when quantum computing came up, it was shown that you can decompose any quantum algorithm, be it as intricate as you want. You can decompose it into 1-qubit gates and 2-qubit gates. But you don't have to. So that's the whole point. So you can. There are other universal gates. There's a Toffoli gate, a 3-qubit gate, or other.
Yes.
So you don't have to decompose your quantum algorithm in these smallest elementary operations. You can use such an all-to-all coupling to speed up certain quantum algorithms. So, for instance, we showed that quantum Fourier transform can be faster than when you use multi-qubit coupling than by decomposing it into single and 2-qubit gates. So you can so if you have all-to-all coupling and you want to decompose it into individual 2-qubit gates, then you have to think of ways of let's say you have 16 qubits and you want to do only a 2-qubit gate, then you have to turn off the coupling for 14 qubits and keep it only for 2 of them, which seems not economic. So,
Yes.
And the other way is you can take advantage of this all-to-all coupling and speed up your quantum algorithm, which there are ways to do that. So,
yeah. But there's probably an optimum size to your artificial spin molecule, right?
Yes.
Like if you make it too big, eventually it becomes kind of untractable to even simulate what's going on in the molecule.
That's completely right. Yes. So so there's a practical limit because your mode structure, your vibrational mode structure, gets too messy. Let's say if you increase the number of your ions in one register, and it becomes difficult to control. So there's anywhere between 2 ions where you can only do 2-qubit gates, and I would say 100 ions where you lose control. Somewhere in between there should be a good register size for certain, and this might also depend on the type of algorithm that you use, which register size is actually the optimal one to implement a given algorithm.
But these ion traps, they are somewhat flexible, right? So you can make an ion trap that can trap somewhere between these 2 and 100 ions, and you can maybe in the future then sort of choose the right amount of ions for the problem that you...
Exactly.
So at what point did you decide to move to Siegen, and what was the motivation behind it?
Okay, so I mean, as a scientist, if you want to stay in academia, there are not too many options actually. So you have to find a place where you think you can realize what you're dreaming about scientifically, and so when I was in Hamburg, it was clear that Peter Toschek was retired, Werner Neuhauser was close to retiring, and it was clear at the time that there was no open position to stay in Hamburg. So I was looking for a different place, and actually there were quite a number of very attractive offers, one from the Science Foundation Ireland. So actually from Hamburg, I first went to Dublin, to Ireland, and then I had also applied for this position in Siegen before, but they couldn't decide at the time. So, but then when we just moved into our house in Dublin, there was a letter in the letterbox with this offer from Siegen, which turned out to be actually very attractive because the University of Siegen made a large effort to building really first-class labs from scratch. So there were no quantum optics labs whatsoever, and they built excellent labs. And yeah, so at the time they only promised to do it, but they kept the promise and they built the labs. And since then there were excellent conditions to do research, and I was and still are very happy there.
And you rewarded them with a Nature paper that sort of developed this ion trap control strategy, like this new ion trap control strategy that you sort of developed, right?
Yes. So there was this. The paper you're referring to is a particular aspect of actually making this whole thing practical by overcoming this decoherence problem in a new way. Using this continuous dynamical decoupling, it was shown how quantum gates can be done with trapped ions that are continuously dynamically decoupled. Yes.
Yeah, I guess we have to shift gears a little bit, and so you have this sort of idea of how to build an ion trap quantum computer, but you actually took it beyond academia into a company, right?
Yeah.
And so in 2020 you started EleQtron, which is Germany's first quantum computing startup. How did you make the decision to go from academia to a startup?
I thought about it already a couple of years before the company was actually founded, and it became more and more clear that if you really want to build a quantum computer, this is not going to work anymore in an academic environment. So it was, doing all the fundamental research to show the principles and to show that it really works. This can be done at the university, but then making a quantum computer really into a useful instrument for other users, for non-physicists, even that requires a completely different scale of resources that is simply not possible in an academic environment. So, so IonQ already existed at the time, AQT existed, and it was clear if we want to bring our ideas into a real quantum computer, it needs different resources, a different environment, and a very focused effort. Yeah, so that was the starting point of EleQtron, basically. Then,
and funny enough, it also now has an office in Hamburg, so that is a little bit of a return. So that's very nice indeed. The reason that EleQtron expanded from Siegen to Hamburg also is because EleQtron is building quantum computers for the German Aerospace Research Center. So the DLR, Deutsches Zentrum für Luft- und Raumfahrt, is setting up this focused effort in Hamburg and in other places in Ulm as well, but trapped ions in Hamburg, and that's the reason why we also set up an effort in Hamburg and now have labs there and people who... So EleQtron is commercializing your particular implementation of an ion trap quantum computer. what will be the business model? What will you sell? Will you sell quantum computers or quantum computer access? What are the ideas?
Yeah, that's a very interesting question. So when we started with EleQtron, the firm idea was to sell quantum computing time at some point, because the thought was most users will not be able or not be willing to really buy a machine, but they will appreciate access to enhanced computing power. But it turned out that the demand for actual physical machines is actually there. So we're doing now both. So we're building quantum computers that are at EleQtron and that will offer soon in the future will offer computing time, and we are also building machines to be delivered to other research institutions.
And where would you say is the company today, and what are its plans for the future?
There are now more than 40 employees right now, real experts from ion-trap quantum computing, but also highly qualified engineers for all these different technological aspects that you need. So it took a very steep development in terms of the number of people, but also the organization itself. It's a real company now. It's with everything you need in a company, as opposed to a university group where you only care about, you have around you are scientists, and there is some administration somewhere, and the administration does everything for you. I mean, they take care of everything that is ideally, and in Siegen actually they do it. They take care of the things that are non-science, and in the company, of course, you have to take care of the whole world all of a sudden. The whole world meaning all the aspects involved in buying and hiring people, and so there are many things. Okay, so current state is EleQtron is a real company functioning with all aspects in every respect. Future plans are to build the best quantum computer ever.
And how, like, you have 40 people now, like how you will grow more in the next years, I guess?
Yes, that's our firm intention, yes.
And what are the limiting factors? Like, what did you discover about limiting factors? How easy is it to hire the right people? How easy is it? More like, are limiting factors more finding the right people or finding funding, or is it really technological breakthroughs? Or do you think technology-wise you just need to sort of engineer things together?
It's all of the above. And yeah, funding, actually, so far, the German government has, and all the agencies and people involved in funding of such research, they are doing a great job in providing, I would say, sufficient funding for research. But then a company, again, cannot live off research. They have to sell things at some point, and so it's a completely. So you also need private investors, of course, to fill this gap that public funding leaves open, and this gap is becoming larger and larger the more the company develops. So private investments are crucial, of course, and this, it seems there is a difference in the way this is approached, for instance, in the US and in Germany or Europe. So in a nutshell, I would say the willingness to invest into long-term risky things in Germany is much lower than in the US. So it's so this is quite a task to acquire sufficient private investments to grow.
Yeah, I mean, the best example is INQ, which had I think literally $1 billion IPO, right? Like they were able to sort of, from the stock market, raise an enormous amount of cash.
Mm-hmm.
But then on the other hand, I mean, when you grow a company, it's really a very fine balance between growing and acquiring, acquiring the, if you grow too fast, if you have this enormous amount of money and you grow, you will also burn through money at an enormous rate. So finding this balance is very difficult, right?
Yeah. So we don't have this problem of having $1 billion available right now. So I'm not sure if I. Yeah.
But I guess you're a Swabian by birth, right? So you will always be good with the money, and that's at least.
Yes, independent of my birthplace, I think. I can handle numbers well, and
maybe just some few last questions.
Mm-hmm.
How worried are you about competition, and is it good that, I mean, to some extent there's some investment in Germany for digital sovereignty, like it's good that you are a German company because the EU will try to keep some quantum computing companies away, in the EU alive.
Yes. Yeah.
So is that an important factor for you? And
yes, I believe that's a very important factor. I mean, if you want to take this, people complained a lot about how Europe is dependent on all these US giants in everything what IT, in every IT respect. And if we don't want to repeat this story all over again, I think it's important to think about what do we need to do now to keep our sovereignty also in the future in terms of these new technologies, in terms of these really revolutionary technologies. Yeah, that's a very important aspect, I think. Yeah.
But yeah, I mean, very impressive. And I think crucially, your company is also in the strategy very different from the competition, right? Like, let's say the way that you build the ion trap quantum computer is really distinct from INQ and Quantinium, for example.
Yes, the physics, the physical principles are very distinct. Yes, and we believe that this has better chances of being scaled up. I mean, otherwise we wouldn't do it. So we are not repeating what others do. We have our own approach, our own path, which is microwave-controlled trapped ions. And so it combines basically the best of different worlds. Microwave control, like in superconducting qubits, and trapped ions, individual atoms that are given by nature in perfect quality. You don't have to manufacture them. So it's a good combination of a new path between the established paths, and I think, it's a highly promising one, yes.
And I think we didn't mention, I mean, you let us visit your lab and the company, which was a very, very nice field trip for us.
Mm-hmm.
Yes.
So thank you for that. What impressed me the most is that in principle this microwave antenna, you just have one waveform generator and a microwave source to control your ions in one register. Mm-hmm. So it's very economical in that respect. And it is really a lot more economical than the laser ion control, right? Like if you compare the amount of money per ion for the gates that you have with the microwave setup than with a laser setup.
Yes, it's economic, but more importantly, I think it's the difficulty of delivering coherent light to any ion at any time in a large quantum computer, because you need, the coherence time of your qubits is in the end limited by the phase stability of the light you deliver, of the electromagnetic radiation that controls the qubit. And if you look at an optical table, there are so many elements, so many mirrors, windows, all kinds of polarizing optics and fibers and everything, and each element disturbs the phase of your light field. And to be sure that you always have a well-controlled phase at any time, at any point in your trap, in your large, if you think about scaling up, it's a large trap with thousands of ions, and to have the right phase at any point in time, at any spatially and time-wise, that's really challenging. And with microwaves, this is so much easier. Yes. So that's, I think, a crucial difference.
But for me, the one thing that I have to say that also I took away is that I also work with microwaves, and my superconducting qubits, they are much less coherent than my microwave electronics. Mm-hmm. But in your case, it's almost the opposite, right? Like in principle, you're almost electronics limited.
Yes, that's if you use these so-called clock states in trapped ions, then the limit is your driving electromagnetic field. So if it's lasers or microwaves, so the limit is the radiation that you use to control.
So your qubit is better than your electronics.
Yes,
yeah. Which is just mind-blowing.
Yeah.
So anyway...
Yeah, we could go on
forever. But thank you a lot for explaining your ion trap strategy, for discussing your career.
Yeah, thank you very much for having me. It was fun.